Good afternoon. Pleasure to be here. My name is Gustavo Rosina, and today I'm going to be taking you back in time. I'm going to be talking about business intelligence, yes, at the Hadoop Summit 2018. As you know, the heyday of business intelligence was between 15 and 18 years ago, but it's having a revival in the context of Hadoop. So folks like me that have been in the industry for a while, we get a chance to undust some skills and a lot of code and put that to work in a new context, which is actually quite interesting, many new problems to solve. I'm going to be talking about interactive BI on Hadoop, which basically means low latency SQL on Hadoop. Until a few years ago, low latency and Hadoop were pretty much opposite, contradictory terms. But a few years down the road, that's no longer the case. Look at Hive, for example. 6 years ago, Hive, as well as Big SQL, they were pretty much wrappers on top of MapReduce. Fast forward to today, and both engines are MPP engines with features like caching, indexing, materialized views, completely different technology, much more advanced, much faster. And that's what makes low latency SQL on Hadoop today a reality. A couple of words about myself. I work at the IBM Canada Lab in Toronto, where IBM makes a number of products, including Java compilers, data science stuff, Db2, a relational engine that you probably heard about, and Big SQL, which inherits a lot of Db2 technology. I'm an architect in Big SQL. I worked on many pieces of it, interaction with HDFS, with Hive, with HBase, ingesting of ORC, integration with Spark. But I'm not going to be talking about any of that today. It's about business intelligence. So that we are on the same page regarding what interactive BI means, let's spend a second on this slide. What is interactive BI? It's a use case. There is a user in front of a screen, presumably a dashboard, a Tableau dashboard, Cognos, MicroStrategy, something like that. And this user is exploring data through the dashboard. The key piece is in the interactiveness. So every time that the user does something on the dashboard to drill down, to aggregate, to look at data from another angle, the dashboard is executing SQL statements on the fly against a server running somewhere. In our case, a SQL server, a SQL and Hadoop server. As you can imagine, that interaction, all those queries have to be pretty fast. That's the key requirement of interactive BI. The latency has to be in a few seconds, or ideally under a second. Otherwise, the experience is not interactive, and the user loses his train of thought, so to speak. Doing that on a large amount of data, and especially if the data is stored in Hadoop, is pretty hard. So we can take a look at, there is a timeline at the bottom, and we can see how the idea of interactive BI on Hadoop evolved over the years. We start with a simplified version of the most common data architecture in many enterprises that starts at the bottom with the operational systems feeding data into the warehouse. The warehouse contains kind of the consistent, sort of normalized single version of the truth. And from that, you can run reporting workloads represented by the little blue printer at the top. But if you want to run interactive BI, you cannot run it on the third normal form data on the warehouse. You have to use an acceleration layer on top, an analytic DB, something like Netezza, like Vertica. And that layer on top, which might be actually part of the warehouse. It might be a different product or an acceleration layer within the warehouse. is not normalized. It's typically denormalized. It uses star schema and many performance tricks because the whole purpose is to get to the low latency interactive BI for the dashboards that are connected above. Couple of years down the road, Hadoop comes into the picture, and even though it was not meant to replace or to be part of the data warehousing environment, that's what happened. So Hadoop was for big data, but people soon figured out that they could offload reporting workloads, as we've shown in the picture, from the warehouse onto Hadoop, which is a lower cost platform. And since the SQL on Hadoop engines have JDBC drivers, it didn't take long for people to try connecting BI tools like Cognos or Tableau to the SQL on Hadoop engine. Of course, the result was disappointment. The statements were too slow. A common solution at the time was to say, okay, let's do this reverse offload or maybe upload. Let's move data from the HDFS into the warehouse so that we can get the interactive performance. Of course, this is kind of backwards because that's what you want to avoid in the first place. You want to offload from the warehouse, and in this case, you are moving data to the warehouse for performance reasons. But you get the performance that you need. If you don't do that, your interactive BI on data that is sitting on HDFS is impossible. So you don't have too many choices. Unless, or actually at the time, some people figured out that there was room to address that pain point with a separate product. And that's when BI accelerators came into market. There is a number of them, products like Jethro, like Kivos, like AtScale. There is also Apache Kylin, which is an open source product. All of them, the whole purpose is to get the low latency on Hadoop data. Without, and avoiding kind of the upload of data to the warehouse. So that keep everyone mostly happy. It's not ideal, but it solved the problem. Briefly, what's the value proposition for BI accelerators? First, as I said before, they let you get the interactive BI performance on data that is on Hadoop. It also applies to big data that is sitting on Hadoop. So you can do now BI maybe on sensor data, on marketing data that would not be naturally stored on the warehouse. Now you can use the BI accelerator to run BI and interactive analytics on that. Some of the tools have a good degree of autonomics. So when you want to get good performance, you need to build data structures on the side, kind of indices, materialized views, and some of the tools do most of that automatically, which is nice. But bottom line, they give you fast response for analytic queries, like the one at the bottom of the slide. That query is a join between a fact sales table and a dimension products, and it's computing the maximum amount of products per category. So this is the kind of the bread and butter query that a tool like Tableau will generate in the background. Of course, not everything is rosy. So the BI accelerator solves the problem, but there are a few downsides as well. Obviously, there is duplication. You have to now license and maintain yet another engine in your data architecture. You need skills to keep the engine going, to tune it, to debug problems, and you have yet another vendor for service and support. Your data architecture gets a bit more complex. Even though you're not copying data to the warehouse, you're still, in some of these solutions, you have to re-ingest all the data into the BI accelerator for it to work. So it's not that the tool will work with data in the open. They need to re-ingest it into their own proprietary format for things to work. And finally, you cannot replace your existing SQL and Hadoop engine. The BI Accelerator is just for the BI queries. You still need to keep your SQL and Hadoop for the reporting queries because you cannot run them on the BI Accelerator. Now you may ask, so what's the secret sauce behind these tools? What is it that these tools can do that SQL engines on Hadoop cannot do? And it comes down to 4 optimization techniques, the ones you see in the slide here. Columnar storage, cubing, also known as materialized views, indexing, and caching. For those of you in the audience that are not too familiar, I'm going to go quickly over them. Columnar storage is how you lay out the data on disk. So in a normal conventional engine, the data for a table is laid out row after row. In a columnar engine, what you do is you take a chunk of rows, maybe 10,000 rows. You take all the values, the 10,000 values of the first column, and you store them on disk. Then you take the 10,000 values of the second column, and you put them after that, and so on. And with that change in representation, you can play a number of tricks that provide a lot of speed up for analytic queries. For example, when data is laid out in columnar fashion, let's say that you have a table with 100 columns, and you're reading only 3 for a query. You can skip scanning the 97 remaining columns. You don't touch them. You just read from disk the columns that you need. In a row engine, you have to read all the rows and just take the columns that you need, but you still have to read all the data. In a columnar engine, you can skip. Another trick is, along with the data on disk, you store some breadcrumbs. For example, for numeric columns, you can store the minimum and maximum value for the 10,000 values. So when you're processing a query, and you know that you're looking for example, rows that are that have a column that says, okay, amount less than 500, if the maximum value on that 10,000 rows is 400, you know that there's nothing there for you to look for. So you can skip just by looking at the minimum and maximum. There is also benefits in compression, because data compresses better when it's homogeneous. And finally, you can do vectorization, which essentially is more efficient machine code to process data in very tight loops. So lots of benefits just from changing the layout of the data on disk. That's a key one. Second optimization is materialized views or cubing. In this case, if you look at the table on the top right, we have a table that has information about sales, with a sales ID, a city, and an amount. And our cube here, or our materialized view, contains the total for each city. Very simple, just for the sake of the example. The way that it is used is when a user that is not aware of the existence of the cube, they just type a query like the one we see there that is requesting sales, the total amount, for example, for a specific city, Toronto in this case. The query optimizer figures out, oh, I don't need to go and recompute that. I have that already. I know that I have it. So I just go scan the cube and find the row that I'm looking for. It's a lot faster than having to compute the sum of all the rows for Toronto in the original table. That you can combine with indexing. So if you create a unique index on the city column of the cube, you can run that query even faster. The optimizer now is about the cube and the index. So the whole query there, it becomes just an index lookup. There is no work done. There is no number crunching and no scanning. Just an index lookup by combining cubing and indexing. And of course, even if the table above had many more columns, in the query we're using only 2. So thanks to the columnar, we would be, when we create the cube, we would only be using, reading 2 columns from disk as opposed to all the rest. Caching, I'm sure that everyone is familiar, but in the BI context, there is multiple kinds of caching. There is data caching, which is the one that we are most familiar with. You put data in memory so that next time you don't have to go back to disk to fetch it again. But there is also statistics caching. Remember that the columnar storage has these breadcrumbs spread across the data. So if you cache them in memory, you can avoid going to disk to fetch a block because just by looking at the stats, you know that block doesn't contain any data you care about. So if you cache the stats, you just read the stats from memory and you don't even go to disk if you know that there's nothing in there for you. And finally, there is query result caching. And that one happens when the same exact query is executed multiple times. That can happen when you run a given dashboard in an organization and there's multiple analysts running the same dashboard. Chances are that many queries will repeat because they are generated by the tool for simple aggregations. Maybe a total sum at the top level of the cube is something that most analysts will do. And the same query will be frequently executed from multiple clients. So querying cache results in that kind of a scenario makes sense. Of course, there is really nothing new about any of these techniques. These are a decade old, at least, most of them. And they have been well known. So why don't SQL and Hadoop engines have them? And it's a question of maturity levels. So when you're building a SQL and Hadoop engine, you go through at least 4 maturity levels. First, you have to get, at the bottom, the core SQL processing right. That is a huge piece of work. SQL is a very complex language. So to implement an engine that understands SQL and that can optimize SQL and give correct results, that takes at least 3-4 years. Once you've done that and you have your fully working functional SQL engine, you want to sell that to enterprises. But your performance numbers don't matter. Or they are not, the only feature that they care about. You need a whole bunch of enterprise features. You need high availability, you need multiple ways of authentication, authorization, and so on. So you have to build all of that before you can sell the engine. Once you sell it, people get happy and more people start to use it. And then your engine crashes because it cannot handle the load. So you have to go back and re-architect your resource management and put maybe workload management in the engine. And only then you have the luxury of looking into interactive BI. But by then you spend like 7-8 years working on the first 3 levels. This picture kind of goes back to the title of the presentation, the convergence of reporting and interactive BI. So the red line represents the performance of BI accelerators. So starting in 2012, which is the center of the graph, BI accelerators had good performance from the get-go. That's because they had all these techniques baked in since the beginning. The progression of performance improvements on the SQL and Hadoop side, which is the blue line, was more bumpy. So things started in 2009 with partitioning. Then at some point, different forms of cost-based optimizations were added, columnar storage, cubing, caching, and so on. Each technology that was added to the engines over the years improved the performance, but it was incremental. So we are now at the point where we are pretty close. I think that is, that's what I tried to capture in the diagram there. Indexing is the one that SQL and Hadoop engines are not strong yet, but some of the BI accelerators are. I think that in the next 2-3 years, there will be a lot of progress in indexing on Hadoop data, which is not yet so mature. So with that as background, let's have a look at some of the most popular BI accelerators in the market today. The first one I'm going to talk about is Jethro, or Jethro Data. This is a SQL engine, but it's not an MPP engine. It doesn't run on Hadoop. It runs at the edge of Hadoop. So it connects to Hadoop from the edge. And it's not, like I said, a multi-node system. It's a single box. The nice thing about it is that it's fairly autonomic. So when you connect Jethro to your data, Jethro will fully index the data, even the measure columns, very aggressively indexing approach. It will create cubes as you execute queries against the engine. So it learns from the queries that you run, which is another nice thing. It's autonomic in its creation of cubes. It also has some level of caching, but the kind of downside of Jethro is that you have to re-ingest all of the data. So Jethro has to represent all of the data in its native proprietary columnar format. And on top of that, it has to create indices on the data. But it's a very interesting technology. The second one is at-scale. Unlike Jethro, at-scale is not an engine. At-scale is just a layer that you put on top of your SQL and Hadoop engine. For example, you may be running Hive, Impala, Presto underneath. You put at-scale on top. And at-scale is a modeling or requires a modeling step. So the first thing you do in at-scale is you define views over your data, and you impose a star schema, sort of, or a snowflake schema on top of your data. At-scale uses that star schema view that you create on top to infer what cubes to create. It also lets you create cubes explicitly, but the modeling step is to get these hints on what cubes or materialized views it should create. And it goes ahead and creates them. But it is, in my opinion, is a much less developed technology compared to Jethro. And again, it's not an engine. It's kind of this modeling tool that, based on the modeling information, creates cubes in the background. So later on, when you query data, you query through the at-scale views. So at-scale has full control of the whole flow. So you're not querying your data directly. You're always querying at-scale views on top of your data. The last solution, which is also fundamentally different from the other two, is Apache Kylin, which is an open source project. You may remember from the 90s and early 2000s the concept of MOLAP engines, which is multidimensional OLAP. That is the same concept applied to Hadoop. So Kylin aggressively creates or pre-computes all possible aggregations on your data. So it requires a massive investment in computing power up front, because then whenever you run an analytic query, all of the possible aggregations are pre-computed. It uses 3 engines under the covers. So Kylin itself is not an engine. It's a very powerful SQL compiler. And it uses Spark to create cubes very aggressively. Then each cube is represented as rows on HBase. So every cell of the cube becomes a row stored on HBase. And when you can throw arbitrary queries at Kylin, and when Kylin figures out that none of the cubes that it has can answer the query, it offloads the query to Hive. So in that sense, it's a complete solution. This slide is about clearing up some misconception that there is around MPP engines on Hadoop. So you may hear claims that being MPP makes an engine unsuitable for interactive BI because it's parallel, and parallel architectures are for scanning, which is not a good, a right perception. If the engine, in addition to being MPP, like Hive LLAP or like Big SQL, they also have materialized views or indexes or caches, the MPP architecture will not be used when you are using these technologies. It will only be used when you have to run a query that does require a parallel join or a parallel scan. So whenever you hear stuff like that, better trust the engineer rather than the salesman. Now let me take a step back and talk about Big SQL. Big SQL is an MPP engine, just like Hive LLAP. It runs on Hadoop, and it's actually deeply integrated with a number of components, as you see at the bottom. It's deeply integrated with a number of components of the HTTP platform. Its most remarkable feature is, coming from IBM, you wouldn't be surprised. It handles complex workloads very well, and it has all the enterprise bells and whistles. Because it has materialized views and indexing and columnar storage and so on, it can support both reporting and interactive BI workloads. On top of that, there is built-in federation, so you can run queries not only on your HDFS data, but on a combination of HDFS data and data that is sitting in your legacy warehouses. And finally, in order to manage the sort of hybrid workloads that combine reporting and interactive BI, remember that interactive BI is about SLAs. You need to respond in a certain number of seconds. So to be able to do that, the engine has to have workload management. With workload management, you can configure the engine to say, I don't want my long-running heavy queries to take more than, let's say, 60% of my engine capacity, because I want to save the other 40% for the interactive BI workload so that I can get my SLA. A quick idea of the difference between resource management in Big SQL and other engines. This is a comparison between Big SQL version 5 and Spark 2.1 from last year. You may be familiar with the TPC-DS benchmark, which is an industry standard. So IBM heavily tuned Spark 2.1 at the time to run Spark the fastest that it could run on a very high-end cluster, and did the same with Big SQL, running on the same cluster. And Big SQL was able to run 4 concurrent streams of TPC-DS at 100 terabyte scale. That's like 500 billion rows in the tables, in 1/3 of the time compared to Spark. And at the same time, using 15% less CPU, 1/3 of disk reads, and 1/9 of disk writes. The benchmark is read-only, but the disk writes are probably for spilling and sorting. So it did a 1/9 of spilling and sorting compared to Spark SQL. So let's see how you would use, how materialized views look in a concrete example in Big SQL. There are 2 kinds of materialized views or cubes in Big SQL. The first one is Hadoop materialized views. We call them MQTS, materialized query tables. I think that the term materialized view was copyrighted at the time, so we couldn't use it. So at the top, you see a materialized view that is pre-computing a 3-way join. So there are 2 dimensions and a fact table there. And the query is computing a 3-way join and is limiting the years to data between 2000 and 2010. So it's really denormalizing data in the form of a materialized view. This could be, this table could be huge. That's why it's stored on Hadoop. And a nice thing about it is that we leverage, as you can see in the 3 lines in blue at the bottom of the create table, we have all the integration with Hive features. The materialized view can be partitioned like a Hive table. It is a Hive table. You can store it as ORC, which is the high performance columnar format on Hadoop. And you can also physically sort the data when you create the table to improve the performance of a feature called predicate pushdown. So if the data is sorted, you can leverage predicate pushdown, which is kind of telling the I/O engine about the predicates in your query, so that data can be skipped based on the statistics in the columnar format. So a query like the one at the bottom the optimizer, when it knows that it has that Hadoop MQT already created, will run pretty fast. I mean, in the from clause, we see that the join is over the same tables. So the optimizer will see, OK, I can use the materialized view. There is a predicate on year, and the materialized view contains years from 2000 to 2010, so 2007 is included. And finally, there is a predicate on the column that we are sorting. So a query that could have taken maybe hours, it might take seconds or minutes using the materialized view. The second kind of materialized view is the native kind. These are really for cubes. These are the ones that we use for aggregation. And the one that we see at the top right there is a join between two tables. It's orders and customers, and it's computing the sum of revenue for each city. In addition to the materialized view, we're creating an index, a unique index on city. This is like the example we saw a couple of slides before. So when we execute a query like the one at the bottom, which it matches, the same tables in the join, the same, and a predicate on city, that query, like the example we saw before, is just an index lookup. The join and the aggregation are pre-computed in the materialized view, and the index gives us direct access to the row we are looking for. So that's how you get interactive BI performance on this kind of queries using materialized views. How do you use that when running, when you try to speed up a Tableau dashboard? The first thing is obviously you tune the engine. The second thing is that you don't want to use your live data when you're designing the dashboard. When you're designing the dashboard, you might leverage the caching capability on Tableau or Cognos. So you bring a sample of the data, you prototype your dashboard on the sample of the data so that you do the prototyping fast. Once you have the dashboard ready for production, you tell Tableau to show you the queries, and based on the queries, you define your materialized views. And once you run the dashboard on production, it will run fast because all the right indices and materialized views are already created. So comparing 2012 and 2018, in 2012, the interactive BI was too slow for SQL and Hadoop. In 2018, we see a green arrow there. So the engine can handle both reporting and interactive BI. It's using workload management to meet the SLAs of both kind of workloads. And it might leverage federation to combine data from HDFS and the legacy warehouses. What are your options for interactive BI in 2018? The first two are the ones we already talked about. The upload to the analytic DB, which is the one that we likely want to avoid. Then the BI accelerators, we talked about the limitations. And now you also have SQL on Hadoop. And SQL on Hadoop also has limitations today, both in Hive and Big SQL, for example. The support for autonomics is not as good as in the BI accelerators, and the indexing is not there. But other than that, all the rest is there. When you have to evaluate what solution to use, there is some homework for you as well. There is no free lunch. So before making a decision, spend the time creating a realistic benchmark that really represents the use cases that you're going to run. Otherwise, you will run into surprises. Ensure that the tool understands the SQL syntax. Ensure that the tool, when it's used at scale, is giving you the response type that you need. And also, when you have an idea of how the tool works under the covers, the stuff that we saw about Jethro, AtScale, and Kylin, try to understand the limitations and play against those limitations. I mean, do you need to create views and rewrite your existing queries, or can you use your existing queries from your existing dashboards as is? How long does it take to tune a given workload? So initially, the workload will be slow. How long does it take for you to tune it? What happens when your data changes? How long does it take for you to ingest new data and update new data in the BI Accelerator or in the SQL engine? A couple of, for those that are interested in Big SQL specifically, a few items in our roadmap. We are looking into improving caching beyond what we have today with result caching. We have to look into autonomics. This is huge. This is very important, so we're going to look into that. Big SQL is integrated with Ranger and Atlas for governance, but only in resource-based policies. We are going to look into tag-based policies as well soon. We have some optimizations around star schemas in the pipeline as well. And finally, you know that Hadoop and Hive have significant changes in 3.0. So we are bringing Big SQL up to speed so that it's fully integrated with the HTTP platform in the 3.0 release as well. To conclude, SQL and Hadoop, there is caching, indexing, cubing, and workload management, and therefore you can do interactive BI. Do your homework when you need to compare the different solutions, and stay tuned. We still have a whole bunch of technologies to undust and adapt to Hadoop. And thank you very much. Any questions?
So for Big SQL, so how is it distributed today? There's no more big insights.
Yeah, the question is, how is Big SQL distributed today? That's right, there is no more Big Insights. So IBM used to have their own Hadoop distribution. That was Big Insights. But as of 2016, we have this partnership with Hortonworks. So IBM stopped having its own distribution, and we only run on Hortonworks today. So it's distributed as a service that runs on Hortonworks. It also, I mean, it installs via Ambari, like the rest of the Hadoop services. So it's fully integrated. It runs under Yarn if you want. The data is on the Hive Metastore, so it's really part of the platform. Can you speak up a little bit? Sorry, I'm not sure if there's a mic. Yeah.
Out of those three options,
yeah.
At scale, and all those three options, which one was tested and what's proven, and which one would be an ideal to use?
Big SQL. No, we have not thoroughly tested the tools. We have not done benchmarks or performance comparisons. We have played with them, but not run benchmarks. So, I mean, like I said when we're looking at that slide, in my view, Jethro is the most mature and interesting. But I mean, it's an engine that runs on the side. You have to re-ingest all the data, so it has pros and cons.
Is Big SQL a paid product, or is that an open source, just like the other?
No, it's not open source. It's a paid product. So it doesn't have any lock-in. So your data is Hive data sitting on the cluster and everything, but the product itself is a proprietary IBM engine, and you have to pay it separately from the Hadoop distribution. And you can purchase from IBM or from Hortonworks. No more questions? Okay, thanks again.